Okay, we're going to cover some Chem 50 stuff. Hopefully it should be review for you. We're going to cover some basic stuff, some applicable stuff for measurements. Um, we'll talk about some types of reactions, and we'll see. Hopefully we get into some concentrations. So I'm just going to go kind of off the top of my head. There's no really prepared notes for these. And again, hopefully it should be relatively review for you. I hope so. Uh, let's just start with the basics here. And one of the first things probably you talk about and is obviously applicable here in lab is measurements, right? And when we take measurements, regardless of what type of measurement you're taking, there's always some degree of uncertainty associated with that measurement. The degree of uncertainty is based on the equipment that you're using. So for example, obviously here, we had something like a ruler. Usually when you use any type of equipment to take a measurement, there's usually two markings you want to look at, and that is the large markings and the small markings. And the large markings typically will actually have numbers written next to them. Like in this particular example here, that is 1, that is 2. So each of the large markings represents 1 centimeter. Let's say we're measuring like this arrow. We then want to count the small markings, which typically do not have actual numbers next to them. They are the markings between the large markings. As you hopefully know, you do want to make sure you count those correctly. We always start counting after the large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we stop at the next large marking. So we have 10 markings between our large marking. Divide that by 10. That means that each of the small markings represents 0.1 centimeter. That's 1.1, 1.2, 1.3. 1.4, 1.5, 1.6, 1.7, 1.8, 1.9 squeezes in there, and then 2. And typically speaking, when you take a measurement, there definitely should be numbers that everybody should agree upon. And those are sometimes referred to as certain numbers. So everybody that looks at my arrows should agree is at least 1.4. And those are our certain numbers. But it's not exactly 1.4, it's not exactly 1.5. And that's really where the estimation or uncertainty comes in. Now, I may look at this and think, well, maybe it's halfway between the two markings. Somebody else may look at it and go, maybe it's a little closer to the 1.5 than the 1.4. And maybe I come up with something like a 5 here, and my units, obviously. That is my first uncertain number. And that would be the proper reading here for this ruler. We would take it to the second decimal place. The reason when we record all the certain numbers plus the first uncertain number, why that's important is, as you may know, that is really what makes up significant figures. So significant figures is basically measurements that are made where you record all the certain numbers plus the uncertain number. This would have 3 significant figures, with the uncertain number in this case being a 5. What you're essentially saying is, I think it's 1.45, but maybe it's like 1.6, maybe it's 1.44, somewhere in that ballpark is where it is. The error here lies in our second decimal place in this case. You always want to look at the scaling because it could be different depending on really badly drawn piece of equipment you're using. Now say this is milliliters, and we have some type of volume in here. As we also know, right, when we read a volume in a liquid, we get the curvature of the liquid. That's known as the meniscus. We always read from the bottom of the meniscus. The reason for that, especially if it's in a U-shaped meniscus like this, is because, as you perhaps learned in Chem 50, it rises up the walls of the container there because the attractive forces between the liquid and the glass is stronger than the attractive forces between the liquid and itself, and through capillary action, it rises up the side. If you didn't have that attraction, it wouldn't rise up the side, and it would be actually at the volume in the middle, which is why we read from the bottom of the meniscus, right? Because that's not touching the walls. It's not affected by that interaction. That's where the true volume is. 99% of the time, that is what your meniscus looks like. You may also perhaps know that sometimes things will give you a meniscus that goes the other way. Mercury is the common one that does that, although you won't come across it too often because they take mercury out of pretty much everything. But in this case, we'd actually read from the top of the meniscus, and the same effect here is happening in this case. The attractive forces between mercury and itself is actually stronger than mercury in the glass, so it actually comes down in on itself and causes that same sort of effect to occur. But probably most of the time, this is where you're going to be reading. You want to read from the bottom of the meniscus. As you may also know, sometimes it's easier in some cases to see the meniscus than in others, especially if you have a really large opening for the container where the liquid is in. That meniscus is going to be kind of spread out, very hard to sort of see, rather than a small sort of opening where you can kind of see it. We would do the same thing here. Our large markings, 10 and 20, that is 10 milliliters. Again, here, if we count starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, we have 10 markings between. In this case, if we divide that by 10, each of our small markings represents 1 milliliter. So that would be 11, 12, 13, 14, 15, and 16, 17. And if we kind of shoot our meniscus somewhere in this ballpark, in this case, we should agree it's at least 15. Again, maybe we think it's less than halfway there. We record something like a 3 in milliliters. This being my certain numbers. This being my first uncertain number. And once again, the estimated digit there is the 3. This also would have 3 significant figures in this case. In general, you could usually go one more place to the right of the smallest marking. Not in all cases. For example, if I had a graduated cylinder such as this, and my water right about there. In this case, our large markings is also 10 milliliters, as that's the difference between it. But when we look at the actual smaller markings in this particular case, we have 1, 2, 3, 4, and 5. We only have 5 smaller markings. And that means that each of the small markings here actually represents 2 milliliters. This would be 12, 14, 16, 18, and 20. So now when I go read my meniscus here, I'm between 16 and 18. The number that comes between 16 and 18 is 17 milliliters. It's the best you could do on this particular scale. That would mean this would have 2 significant figures, and the uncertain number would be the 7. Yeah, so a lot more error sort of with that measurement. So this would be a case, obviously, you cannot go one more place to the right of the smallest marking, but in a lot of cases you can. One way, if you're not sure how far you should take the reading to, but you are very confident in, I think the smallest markings represents this amount, you could always take the smallest markings, for example, and divide it by 2. If you take the smallest marking divided by 2, that gives you plus or minus 0.05 centimeters. In reality, what that tells you is I should take the reading to 2 decimal places, which is exactly what I did here. I'm able to do that based on that. That gives you sometimes what is referred to as a tolerance or uncertainty in that measurement. You could also do it for this guy divided by 2. Smallest markings gets you a plus or minus 0.5 milliliters. That is 1 decimal place, which is where you should take it to. And by the way, you could even do it for this guy, divide that by 2. Gives you plus or minus 1 milliliter, which is the whole number that you took it to. So if you're ever unsure, but you are fairly confident in, I think each of these small markings represents this amount, you could just divide it by 2 and it'll give you basically how far you should take the reading. If you divide it by 2 as a whole number, take it to a whole number, 1 decimal place, 1 decimal place, or 2 decimal places. Also a reminder that it's really important when you, and maybe we'll just steal, we'll steal this guy right here. Let's just say, let's say we had something that we're measuring, which always happens in lab, right? And let's just say it is like dead on that mark right there at 1.4. So clearly we went through this a second ago. That is 1 centimeter large markings, 0.1 centimeter here. I would record perhaps 1.4 centimeters, 1.40 centimeters, 1.40000 centimeters. Is there a difference in how you record it? Doesn't matter. The answer is it does matter. Let's just take this one for example. That is how many significant figures based on that measurement? That is 2. The uncertain number in this case then would be the 4, right? So when you give that measurement, what you're saying is, I think it's 1.4, but maybe it's like 1.5, maybe it's like 1.3. That is like this much error you just put into that measurement. That's a whole football field of error, right? That you just basically threw in there. And that's clearly nowhere near where the marking is, right? You can clearly see on the scale there, there's much closer to that. So we wouldn't want to do this and drop a 0. That's kind of important. If we take this guy, how many significant figures does it have? It has 3 significant figures. The 0 here, right, is the uncertain number. So when you do that measurement, 1.40 centimeters, you're basically saying, I think it's 1.4, maybe it's 1.41, maybe it's 1.39. That is basically, if we look at our scale here, that is an error right about there, yeah? Which is essentially what we got going on this particular scale. So we would want to definitely record it in this case. And that's a very common thing. Sometimes people do, if it's right on the number, they lop off a number thinking, not that important. It is really important because you're frankly making your calculation or really your measurement and ultimately your calculation probably a lot worse than it should be based on the equipment you're using. You're pretty much making a crappier measurement than you should be able to do on that piece of equipment. The other here, by the way, is also not a good thing, right? Because basically what I just did when I put all those extra zeros to make it look more chemistry-like, right, is I now made that measurement way better than it ever could be based on the equipment that I'm using, right? I have now moved my error all the way down to how many zeros I put there? 2, 4, the 6 decimal place is where I put the error, when in reality it actually should be at the 2nd decimal place. So when you take a measurement, you do want to record everything properly to the proper number of significant figures based on the equipment that you're using. Because again, if you kind of lose some numbers, you're making your measurement a lot worse. If you add extra zeros where you're not supposed to, you're making it a lot better than you should be. You do want to obviously give the measurement to the proper number of digits. Any questions on measurements there? By the way, when we use something that is digital, that gives you a digital reading as a measurement, all those numbers are important. So you should record all those numbers. Very commonly, people go to the balance and they just record like 52 instead of like 52.345, whatever it may be. You do need to record all the numbers. They're there because they're important if it is a digital display. So you should record all the numbers. I sat there all day, Professor. I did, like taking one little crystal out at a time to make sure I got exactly on the nose. By the way, sometimes people get suspicious if you're always right on the number exactly every single time. Extremely hard to do, by the way, yes, unless you take all day doing it. So just keep that in mind. All right, so obviously when we take measurements, we do want to make sure we do take it properly and we do record things to the proper number of digits. In general, if you're using anything that's volumetric, that has basically one marking, like a volumetric flask, a volumetric pipette, usually 2 decimal places is usually how far you kind of take the reading to. With that being said, we talked about sig figs here. Let's talk officially about, again, a reminder how to calculate or count sig figs. So starting with all non-zero numbers, right, are significant. So all non-zero numbers are significant. So if we had 1, 4, 3, 5, obviously that would have 4 significant figures. Zeros is the thing that gives people a lot of trouble. So there are leading zeros, which are not significant, and 0.00323. All these zeros that come before the very first non-zero number are considered leading zeros and they're not significant. So in this case, these three here would be our three significant figures. Remember that when you're counting significant figures, you go left to right and you start counting at the very first non-zero, and that is where you should start counting your significant figures. There are trap zeros, captive zeros, whatever you want to call it. Those are significant, and those are zeros that are between two non-zero numbers. So if you had 4004, we would start counting here. These would be significant, and obviously that would be as well. That would have four significant figures, that particular number. Probably the zero that gives everybody the hardest time is the trailing zero. Yeah. And that may or may not be significant. And what determines if it is significant is there a decimal point in the number? And it does has to be written. So is there a decimal point in the number? The answer is yes, then it is significant. If the answer is no, it is not significant, those zeros at the end. So if you had 600 written like this would have one significant figure, and it would be this guy right here. These are zeros, there's no decimal point in it. The uncertain number, by the way, would also be the 6, and you're basically saying, I think it's 600, but maybe it's like 700 or 500. That is, again, a really crappy measurement, frankly, because that's a lot of room for error in there. If I go 600 and I lay me up a decimal at the end, I now have three significant figures, as these are all going to be significant. The uncertain number would be the last zero in this case. Much better measurement, because now I'm saying I think it's 600, maybe it's 601, maybe it's 599, so a lot less room for error. Whenever you can use any type of device that can move your error or uncertainty to the right, it's a much better measurement, right? So it falls way, way shorter down the road there. So if I had 0.0040032000600, how many significant figures does that have? We'll just say that was some type of measurement. I'm not sure how you get that. But how many significant figures would this one have? I'm not even sure either because I was just writing numbers. So let's take a look and see. Seems like a lot of numbers on the screen. All right, let's start with it here. These guys here are not going to be significant because we have not hit the very first non-zero. That's where we're going to start counting. Those are trapped, which makes them significant. So good, 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 good. Another set of trapped. So those are good, good. So that does leave the zeros at the end. Are they significant? The answer is yes, because way over here, there is a decimal point. And the decimal point does not need to be near them. So let's see what we got there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sounds good to me. 10 is like a winner there. Any questions on counting significant figures there? Sort of with that as well, sometimes the way that we write numbers in chemistry is scientific notation, right? And scientific notation properly done is n times 10 to the n, where that is a number between 1 and 10. It could be 1, but it can't be 10. So it could be 1 point something, but it can't really be 10. And this is either a positive or negative number, depending on which way you need to move it to get it to a number between 1 and 10. So if we had 1, 2, 4, 6, and we want scientific notation, although it's not written there, we would assume the decimal point would be there. We'd go 1, 2, 3 places. 1.246 times 10 to the 3. We had 0.0042. 1, 2, 3 places. 4.2 times 10 to the minus 3. Positive exponents if you move decimal to the left or you have a large number. Negative exponents if you move the decimal to the right or have a small number. By the way, if you're comparing negative exponents, This smaller negative exponent is actually the larger number, right? So just keep that in mind. In terms of scientific notation, whenever you write a number in scientific notation, all these numbers are significant. So sometimes the only way you could get the answer to the right number of significant figures is to write it in scientific notation, because you could essentially control the number of significant figures. So for example, this one would have 4 significant figures, this one would have 2 significant figures. But let's just say, for example, I needed 3. I could just do this, and now it's got 3 significant figures. So all the numbers before the times 10 part are always significant when you write it in scientific notation. And again, sometimes the only way to get the answer correctly is to do that. You do not need to write it in scientific notation for everything that you can, but you do need to try to get to the right number of significant figures. Speaking of scientific notation and like lab reports and stuff like that, a lot of times on calculators and stuff, we do use E for a scientific notation or times 10 part. When you do give an answer, you should not use that when given an answer. So for example, there you should write like I did below, 4 times 10 to the minus 3. You should not write 4.2 e minus 3. So don't write it like that. Write it like that if you're given an answer. Even though on computers and stuff like that, we do use that to represent the times 10 part. When displaying that in data or something like that, you should definitely not use it. Speaking of calculators, probably more important than writing these things in scientific notation is to know how to properly punch it into your calculator, which a lot of people surprisingly do not know how to do. So when you're doing scientific notation on your calculator, most calculators have an actual exponent button. It's an EE button on a lot of calculators. It's an EXP button on a lot of calculators. And if you have maybe like a two-tone calculator, 2 different colors, you may actually have a times 10 to the n and an actual wheel that's usually right next to it on there. And these are actually your exponent buttons, how you're supposed to punch it into your calculator. Other important buttons, this is what I call your negative button, but change the sign button, are on calculators sometimes like that. So when you are punching something into the calculator, you want to make sure that you do it correctly. So if you're going to punch this in, we'll talk about these buttons first. You would go 6.25, you would hit your exponent button. That will pop in 6.25 on your display, probably an E, or you may have on your display a couple of zeros to pop up, or maybe like times 10 in there as well with it. Once you do that and you hit the exponent button, when you hit this button, it represents this part of the number, which means you should not use the multiplication button unless you don't want to get the right answer. You should not use the inverse log button, which a lot of people like to use, because above log on most calculators it says 10x. People think that's like the exponent button, and it's not. All you have to do is hit the negative button at this point, and 6. And that'll go -6. We'll put a negative and turn that into a 6. And that is the proper way to punch something into your calculator that's in scientific notation to get it. Now, if you have a two-tone calculator like this one with the wheel, you have to do a couple of other steps along the way. Otherwise, your calculator, for lack of a better description, is programmed crappily, right? So it's not programmed so well. It will do the math wrong if you're not careful. What you have to actually do is you actually have to put parentheses around every number that's in scientific notation. So if you're going to do this, you would have to open up a parentheses and go 6.25. And what it would show on your calculator screen is a parentheses 6.25. You then, very much like everybody else, can hit the exponent button. It will pop a 10 and a caret. And what you'll have at that point is a little cursor kind of blinking towards the top. And if you have that cursor blinking towards the top, you can do the rest of it. You hit your negative button and 6, and it will then become something like this. And now your cursor is blinking to the right of the 6 in this case. The problem with that is your cursor is up on top and not on the bottom where it should be. And if you close the parentheses in this case, you'll get a small little, if you kind of close the parentheses, you'll end up with something that looks like this. And if you try to hit equals, you usually will get an error on most of those calculators because of that. So what you have to do is actually bring the cursor back down. That is where the wheel comes into play. You just hit the right-hand side of the wheel. That will send your cursor back down to regular size, if you will. And now you'll have a blinking cursor like so. And now you can close the parentheses and you'll end up with, obviously, your number there in proper scientific notation there. And again, it's a lot of steps. I drew it out step by step, but obviously if you understand how to do it, it can go obviously super quick. And that's basically what you want to make sure that you do punch these numbers in correctly. We will have a lot of numbers throughout the class that's in scientific notation, and a lot of people screw it up when they try to punch it into their calculator. So you do want to be really careful when you're doing that. Also, you usually do not want to punch too much into your calculator at once. That is also another very common sort of problem. So for example, if you're doing some type of calculation where you have a number times a number times a number times a number, and then you're going to come back basically and divide it by a number, right? Divided by a number, divided by a number, divided by a number. So what you should do is basically you can multiply as many of these numbers as you want at one time. You should then hit equals after it. Call it number 1, number 2 on the bottom, number 3, number 4 on the bottom. What you then should do is hit the divide button and then divide by number 1 and then hit equals. Then hit the divide button and divide by number 2 and hit equals. And hit the divide button and divide by number 3 there and hit equals. And one last one there, divide button and number 4 and hit equals. And you will always get the right answer. My experience, people, when they try to punch too much at the bottom on there at once and they do not use parentheses correctly, the calculator again does the wrong math. So you'll never get the wrong answer. If you have a bunch of numbers, you got to go back through and divide by each one individually, hit equals in between, and you will get the right answer. Any questions on calculator, scientific notation? Definitely skills that come up in lab and also lecture as well. Speaking of measurements, there is definitely a difference between accuracy, right, and precision. So if you're accurate, that means that you are close to the true value. If you are precise, that is how close a set of numbers are to one another. So the classic example is throwing some darts. When you throw darts at a dartboard, the goal is to get the middle there, the bullseye. So if I throw some darts and I end up over here, maybe over here, am I accurate? No. Am I precise? No. I missed the board twice and probably hurt somebody twice. Maybe 2 different people, right? All right, so I go double or nothing. I pick up my darts, maybe my pride, and I throw it again. And I go boom, boom, boom. Am I accurate? I am not, because again, the goal is to hit the middle, right? Am I precise? Yes, I'm precisely not accurate, right? So you can be very precise, right? And you could do the experiment multiple times and do it multiple times the same way wrong every single time, right? And get the same result. So that's not a good thing, right? So again, I go triple or nothing. You shouldn't have bet, obviously. I go triple or nothing. I lay my darts there. I go boom, 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 right? Am I accurate? Yeah. Am I precise? Yes, I am both of those things. And that really is the goal, right? When you do experiments, for example, you do want to be accurate. You do want to get the right answer. You do want to be precise, which means that in a lot of cases, is the experiment reproducible? And that's why, for example, we do multiple trials of something, right? To see, can we reproduce those things? Can we get the same number every single time, or how close the same number is to each other? When we talk about accuracy, a lot of times we talk about calculating percent error, like your experimental minus the true value divided by the true value times 100%. When we do a percent error, do we want a high number or a small number? We do want a small number, not to be confused with percent yield, which we want a large number, right? So small number and percent error, large number means you just did it really crappily, right? But you did a very nice job. I had 400% error. I did it 400 times worse than everybody else, right? So you do not want that. You want a small number. Precision, we look at things like, for example, standard deviation, percent standard deviation. So those are things sometimes that we calculate, for example, in the lab to look at precision versus accuracy. And again, a lot of times we do multiple trials to help us understand those two things. Speaking of calculations, obviously you do want to give your answers to the proper number of digits. So let's just talk about sig figs and calculations. If you multiply or divide, our answer, we are looking at significant figures. And it is the least number of significant figures. So when you're doing a calculation, whichever number has the least number of significant figures is how many significant figures your answer should have. So if you have 42.1 times 32, this has, again, 3 significant figures. This one has 2 significant figures. That means my answer should technically have 2 significant figures. And if I do that, 42.1 times 32 on my calculator, what I get displayed to me is 1347.2. A reminder that your calculator does not usually give it to you in the right sig figs or scientific notation unless you have a program to do so. In this case, we would want to go to 2 significant figures. Normal rounding applies here. This should be 1300 perhaps, yeah? Why should I not drop the zeros? Yeah, because 13, right, is 2 significant figures, but it means something very much different than 1300. If you don't understand that, imagine I owed you $1,300 and I said, here's 2 significant figures, here's 13 bucks, right? You're not going to be really happy with me, right? So we never want to, when we round, right, change the meaning of a number by trying to get the right number of significant figures. We also obviously could do scientific notation on this one. We do a 1.3 times 10 to the 123, right? 2 sig figs right there as well. So that goes with multiplying or dividing. That's what you look at. Sig figs, least number of sig figs. That's what your answer should be. If you add or subtract, here we look at for our answer, it is the decimal places. And it also is the least number of decimal places. So if you took 4.222 and added it to 1.33 and added it to 2.1, try without the calculator, 2, 5, 6, 4, 6, 7. This is decimal places we're looking at, which is 3, 2, and 1. That means that is where we should go. Here we look at the 5, and we should end up with 7.7 as our answer. That, by the way, has 1 decimal place, but how many significant figures? It has 2 significant figures. And that can be important if you combo some calculations, right? If you take that number and you're going to use it in another calculation, maybe multiplier and dividing, you got to switch from decimal places to significant figures, and sometimes it has to go vice versa. Remember that if you do combo, you do want to kind of keep track of everything along the way. So if I took 42.66 times 0.320 and divided it by 46899, here we would do what's in the parentheses first as multiplying. That has 4 significant figures. This has 3 significant figures, which means technically speaking, when we're done with the top part, we should end up with 3 significant figures. The next thing we would do is take the top part divided by the bottom, which has 5 significant figures. So we're ultimately taking 3 sig figs divided by 5 sig figs. That means our answer should end up with 3 significant figures based off of really the first calculation we did. So you do have to keep track of what you're doing along the way. And eventually cleaning it up there at the end to the right number of digits. Now, should you round along the way? The answer is probably not too much. Yeah. So you should probably keep a few, what they sometimes call guard digits or extra digits. And you should avoid rounding to the very end, but you do need to keep track of what you're doing so that you can clean it up correctly at the end. But it definitely don't want to round, because if you round really strictly at the first step and you're taking that number and get an answer, round again and take it and do something else with it. Every time you round, you're moving yourself further and further away from probably the true value and stuff like that. So you don't want to round, keep some extra digits, just roll through. If you need to write it down, just write a couple extra digits or so, and usually okay, 2 or 3, and you usually should be fine in terms of rounding errors. Any questions on that there? All right, then next important thing, right, is our friend molar mass. Yeah, if I could spell it there, mass, there you go. So molar mass is units of grams per mole, right? We can find the molar mass there on the periodic table. It is that number that's on the bottom. That is the atomic mass in AMU, and it's also the molar mass in grams per mole. So if we have hydrogen, that means in 1 mole of hydrogen, there is 1.008 grams, and the molar mass of hydrogen would be 1.008 grams per mole. We could use it as a conversion factor, 1.008 grams over a mole, or you could flip it around if you're going to do a little dimensional analysis, and you could use it like so. Molar mass is really the conversion factor we use to go from 2 units, really, grams to moles, and moles back to grams. By the way, that is the abbreviation for moles. That is not molecules, right? So if they want molecules, they will write it out. So you use the molar mass to go back and forth. You have something that is a bunch of stuff together. You just go to the periodic table and find all those things, and you add up all the parts. So that would be 2 times 1.008 grams per mole plus 16 for the oxygen. Gives us a molar mass of water of 18.02 grams per mole, which once again you can use as a conversion factor to, again, do those conversions. Obviously, if you have grams and you want moles, you divide by the molar mass. We are multiplying here and then dividing what's on the bottom. Because you're dividing grams divided by grams, they cancel. You're left with moles. If you start with moles, you're going to be multiplying by the molar mass, grams per mole. You're going to multiply basically and divide. Once again, here you're dividing the moles out and you will be left with grams. So that is, again, our conversion factor that we go from grams to moles or moles to grams. We do use that a lot, especially in lab, right? You have to figure out how many grams you need to weigh out or something like that. So that's a very common sort of thing. Maybe a little less common is Avogadro's number. We don't really use it all that much, but why not do a shout out to him, right? So 1 mole of anything will equal 6.022 times 10 to the 23. These could be atoms. These could be molecules, particles, pizzas, whatever you like. But typically use Avogadro's number as a conversion between moles and atoms are molecules, and backwards, right? So that's usually what we use Avogadro's number for. All right. Any questions on that, right? All right. Next kind of important thing to remind you are chemical equations. Chemical equations are how we represent chemical reactions, which are chemical changes that occur. And a reminder, on the left-hand side of the arrow are our reactants. That's our starting material. On the right-hand side of the arrow are our products, which is what is formed as a result of the chemical reaction. We oftentimes will use solid, liquid, gas, or aqueous as symbols next to formulas in these equations. Solids obviously in the solid state. L is liquid in the liquid state. G is gas in the gas state. AQ is aqueous, which is a water environment. And there is a difference between aqueous and liquid. Something that's a pure liquid is something like water is a pure liquid. It's a pure substance. There's nothing else mixed with it. If you take a pure substance like water and you add some sodium chloride to it, the sodium chloride will melt, not melt, will dissolve, and you will get a sodium chloride solution, right? Which is made of a solute and a solvent in this case. And it's actually a mixture, is what something that is aqueous is. It's a homogeneous mixture, looks the same throughout, which is what a solution is as you go through there. Speaking of that, right? So when we have an equation, it should always be balanced. So if we had something like sodium metal plus some chlorine gas, maybe it makes a little sodium chloride along the way there. Put a little 2 there, right? And a 2 there. Remember, we balance the equation. We only change the coefficients. It's the only thing that you could change. You don't change the subscripts or anything like that. Otherwise, you change what it is. When you have a properly balanced equation, all these coefficients need to be whole numbers, and they need to be the simplest set of whole numbers. So for example, if you balance the equation with these as your coefficients and it was all balanced, you could actually go through each of these coefficients and divide by 2 and still get whole numbers. And this would be really your properly balanced equation in this case. So there has to be whole numbers. Remember that sometimes you may have to use a fraction to balance the equation, but you do have to clear the fraction when you're all said and done to make sure. Speaking of that, along with reactions and molar mass and grams and moles, everybody's favorite stoichiometry, yeah? Or not. Remember that you can look at this equation and the coefficients can be thought of as the mole to mole relationship. You could say, for example, 2 moles of sodium react with 1 mole of chlorine. You could say 1 mole of chlorine react to give you 2 moles of sodium chloride. 2 moles of sodium gives you 2 moles of sodium chloride. So these are what are referred to as the stoichiometrically equalities. And from any of these equalities, you could write 2 conversion factors. 2 moles of sodium over 1 mole of chlorine are 1 mole chlorine over 2 moles of sodium. So in a basic stoichiometry problem, for example, if you knew how many grams of sodium you started with, you want to know how many grams of sodium chloride you would produce. The steps that you would follow in this case is you would take the grams of sodium and convert to moles using the molar mass to do that, right? In most cases. Once you have that, you would then find the mole to mole relationship between these two. And by the way, before you start anything, you always need a balanced equation, right? Otherwise, stoichiometry doesn't work. So you always need a balanced equation to start with. And in this case, we have 2 moles of sodium gives us 2 moles of sodium chloride. So, if you had 5 grams of sodium, you would use the molar mass from the periodic table, 2299 grams of sodium per mole of sodium. That will cancel out the grams of sodium. You then would do the mole to mole relationship. 2 moles of sodium gives you 2 moles of sodium chloride. That will also cancel out the moles of sodium. Then you would need the molar mass of sodium chloride, or the formal mass if you want to get formal about it. And that would be, in this case, 2299 grams per mole from the periodic table, plus 3545 grams per mole for the chlorine from the periodic table. Going to give you a molar mass there. We'll go with 5844. or sodium chloride. That's what you would use here in our last step. Grams would go up on top, 58.44 grams per mole of sodium chloride. Those will cancel, and that will give you your answer, what we would produce in this case, which would be in my made-up one here at the last minute. Looks like about 12.7 grams or 13 grams we'll go with. Grams of sodium chloride would be produced. By the way, that number that's produced is known as the theoretical yield, right? And that is based on the equation of stoichiometry, how much you start with. That is your maximum yield if everything went perfect, no side reactions occurring. That would be your theoretical yield, right? By the way I set it up, that is also something you should be familiar with. That is what we call dimensional analysis, right? And that is the way that you show your work. I like parentheses. Some people like logs, they call it, right? Or whatever they call it. I don't know. But basically, if you're not familiar with this is all opposites cancel, right? Top, bottom, right? So everything on top gets multiplied, and everything on the bottom gets divided. So when they say show your work, usually this is what they mean, yes. And again, that is what happens in dimensional analysis. Also, the nice thing about dimensional analysis is you may not even need to know a formula. You can just get rid of the units you don't need and get the units you do need. You can probably figure it out. Also, you always multiply and divide, which means your answer should always be based on significant figures, right? Remember that if we have exact numbers, which are things that are counted or definitions, especially metric to metric or English to English, we don't worry about those when we're thinking about sig figs. It's only really measured numbers that we do. Any questions on that? That is basic stoichiometry. There also is limiting reagents, right? Or reactants, depending on what they called it when you got taught. There's limiting reagents and excess reagents, right? And that is because in every reaction, there's usually one reactant that gets used up first, and that is the limiting reagent. And the one that you have plenty of is known as the excess reagent, is the one that you have left over at the end of the reaction. By the way, why is limiting reagents important? Which one determines how much product you make? Is the limiting reagent is always the one that determines how much product you make. I won't go into how you determine that. There's multiple ways, including ways that are never really taught in Chem 50, which is they should be because it's much easier to do. But I would say probably this day and age, the most common way people are taught is to do two separate calculations, right? And see which one produced the least number of product. Is that pretty much how most are taught these days? It's a terrible way. No, nothing wrong with it, but there's much easier ways to do it. The way you know it is a limiting reagent problem, right, is if you can get to moles of each reactant, right, based on the information given to you. So if you have some information given to you for each reactant that's present, if you're able to, just with that information, get to the moles of each reactant, you do have to figure out the limiting reagent. And obviously, once you do figure out the limiting reagent, you would want to use that to figure out how much product you made. Any questions on stoichiometry there? All right, then rolling through here. Not bad, almost on pace. We'll see. Let's talk about types of reactions and ways to classify reactions. As you may know or may not know, let me tell you, is there's really three reasons why a reaction takes place, right? The three reasons why a reaction takes place is you formed a precipitate or a solid. You formed water. Or there was some type of electron transfer. Ultimately, most of every reaction breaks down to one of those three things occurring as to why it's actually taking place. There's really two big categories of reactions. There is double displacement reactions, which we see a lot in this class. And those have the general form of AB plus CD. These are two ionic compounds, which means positive, negative, and always in this situation, they switch partners and they make new ionic compounds on the other side. It's not that. Let me get my alphabet right here. Try that again. They will make A and D and C and B in this case. And double displacement reactions actually take care of the first two reasons. Now, when you do this, you can make what is sometimes more commonly referred to as a precipitation reaction, where you basically put together something like sodium chloride, a little silver nitrate, positive, negative guy, positive, negative. We're going to switch some partners here. Going to make a little silver chloride, a little white solid there, and a little sodium nitrate action happening. There's our precipitate. Reason number one why this reaction took place is the formation of that precipitate. Acid-base reactions, which we do a lot in this class, we basically make something like, for example, hydrochloric acid plus some sodium hydroxide. That is an acid base. It is also a double displacement reaction, positive, negative, positive, negative. They switch partners, makes you a little sodium chloride and some water. Lo and behold, that is water. Step number two, why a reaction takes place. Usually get if you take a strong acid and a strong base and put them together, you usually get a salt, which is the sodium chloride, an ionic compound, and water is formed. So double displacement reactions are more commonly classified specifically as precipitation reactions, which results in some type of solid form, are acid-base reactions, which forms water, which is sometimes why they're referred to as acid-base neutralization reactions, because you basically make water. You could go through these reactions and do, dare I say, a total ionic equation, net ionic equation, and find some spectator ions, which we do a little bit in here as well. But you'll get, in the case of the acid-base reaction with a strong acid, strong base, is always the formation of water, which again is ultimately sort of what's happening in that particular case. Now, what about electron transfer? That is basically under the other big umbrella of reactions, which is our favorite things, redox reactions, which you might have touched upon in Chem 50. Redox means oxidation, which means lose electrons, and reduction, which means gain electrons, right? Some people remember that oil rig, our Leo the lion goes grr, whichever one you like there. We'll do that for you. But in each of these cases, these are really electrons being transferred is the idea here. We have a transfer of electrons. And more specific classifications of these type of reactions that you might be familiar with, we have our synthesis reaction, our combination. Two things make one thing. Decomposition reaction. One thing breaks down into two or more things. So like the one I just did there, a little sodium plus some chlorine, make some sodium chloride. Water, if you run an electrical current through it, will make hydrogen gas and oxygen gas. And I'll do a 2 and a 2 there. Also, single replacement reactions. Single replacement reactions have A plus B, C. This could be a metal, bless you, or a non-metal. And if it happens to be a metal, for example, the metal will replace the positive guy and make a new ionic compound and kick out that positive guy that will not have a charge in this case. No charge on any of those. By the way, if it's a non-metal, it'll actually kick out the negative guy and make a new ionic compound. And C would come out with no charge if it was a non-metal. By the way, in order for that reaction to take place, whatever is coming in needs to be more reactive than what is replacing, right? If it's less reactive, that reaction will not take place. Lastly, our combustion reaction is under this category. Just so you know, in order for it to be a combustion, that's pretty much all you need, some oxygen. But most people, when they think about combustion, they think about the organic combustion, which is an organic compound that's carbon, hydrogen, maybe oxygen, plus O2, a little CO2 plus water. And that's more of an organic combustion. So pretty much all reactions fall into these two umbrellas, and they account for all three reasons why a reaction takes place. We definitely will hit some redox reactions when we get into obviously the electrochemistry chapter, but a lot of the acid-base early stuff is a lot of double displacement, acid-base reactions that we see a lot of. So you make sure you will know those and how to write the reactions if you only have reactants given to you. And that's super common in problems. They'll just tell you, hey, these two things are there. They won't tell you anything else in a problem. You're going to have to come up with the actual products and balance the equation. Any questions on that there? All right, last couple of things here to talk about that's kind of important. Solutions, right? And solutions, as I mentioned earlier, are things that typically get the aqueous symbol. They are homogeneous mixtures made up of two things, the solute, which is the small part of the solution, and the solvent, which is the large part, right? Things typically make solutions when they both have the same intermolecular forces, like they're both using hydrogen bonding, dipole-dipole, dispersion forces. Perhaps you heard of like dissolves like. Yes, maybe. I don't know if they teach that still. But things that use the same type of intermolecular forces will be very soluble in each other, tend to mix and make solutions. Now, when we have a solution, probably the most common thing for a solution is concentration, and probably the most common concentration unit that we use is molarity, which is big M, right? So molarity is equal to moles of solute divided by liters of solution. It is a formula that hopefully you know because we will use it a lot. It is molarity is moles per liter. We could rearrange this. Liters is moles divided by molarity. Moles is liters times molarity. You definitely want to, if you're doing this calculation, make sure that you do convert the volume into liters because you're probably shooting for moles in whatever you're doing. What happens if I take milliliters times molarity? What do I get? Do I get moles? I do not. I actually get millimoles, which will probably put you about 1,000-fold off of what you're thinking it is. Yeah. So you can do that, but you got to understand it is millimoles that you get and not milliliters. So when we have something that is the molarity of something 4.5 big M, when you're doing a calculation, as you probably were taught, is probably a really good idea to get rid of the big M and basically turn it into a conversion factor, 4.5 moles per liter. The number always stays with the moles part. It's always per 1 liter, or a liter is 4.50 moles. That way, for example, if you have 32 moles of something and of sodium chloride or whatever this may be, you could use it with dimensional analysis. Again, go opposites. Moles on the opposite side there per liter. Moles will cancel. Once again, multiply, divide. By the way, by just doing that, I don't even have to worry about rearranging, right? So I already know what I have to do here. Why should you get rid of the big M? Because in my estimation, people have no idea there's even liters involved. They forget all about the liters part of it. They think M and think moles and stuff like that. So I definitely take a more dimensional analysis approach when you're doing these calculations so that you can visually see the liters part of it or the volume part and know how to do it. With that being said, another very common thing that we do in here is dilutions, right? Dilutions is when you add more solvent, right? A lot of times people say when you add more water, but water is not always the solvent that is used, right? Water would be a terrible solvent for something that is non-polar because water is polar and can do hydrogen bonding. Non-polar things can only do dispersion forces. They are not going to interact with themselves really well. You would need a non-polar solvent like hexane, which is non-polar, or something like that. So when we add more solvent, we have an equation, which is a dilution, M1V1 equals M2V2. This is typically before the dilution. This is usually after. Some people learn the classic C1V1 equals C2V2. C is concentration. You can use technically any unit of concentration you want in this formula. You use percent mass to mass, percent mass to volume. But most people will roll with M1 V1 equals M2 V2 because molarity is the most common unit of concentration that we come across. So we do that. Why does the molarity get less when you dilute something? It is because of the definition of molarity, which is moles of solute, liters of solution. Remember, the solution is the solute plus the solvent. So when you add more solvent and you do a dilution, you're basically making this bottom number larger, which makes your molarity go down. Yeah. Bottom number goes up, molarity goes down. So typically we dilute something to make it less concentrated than where it started with. Typically, this is the more concentrated molarity. This is the volume of that solution you would need. That is the molarity of the solution you're trying to make, and that's the total volume of the solution that you're making. If you do use M1 V1 equals M2 V2, this is the one equation where you can leave, if you want, the volume in milliliters, and it will work out okay. And that is because, for example, if you solve for M2, that is M1 V1 divided by V2. If I put just the units in, molarity, milliliters on top, milliliters on the bottom, they cancel and you're back to molarity, by the way. And it works the same thing if you were solving for volume as well. If you're solving for V1, that would be M2, V2, M1, which should be put into units, M, milliliters, and M. Those will cancel. You'll be back to milliliters in this particular case. That's what happens, by the way, when we were talking about earlier. If you take milliliters times molarity and you get millimoles, if you then divide it by milliliters, the millis cancel. You're back to moles per liter, and you're back to molarity. So if you want to do that with that equation, you can. You could leave it in milliliters. If you want to convert it to liters, you can. The only difference is if you convert it to liters, the volume you get will be in liters, or if you leave it in milliliters in this equation, you'll get milliliters. You 100%, though, as we talked about a second ago, doing this calculation, you need to convert it to liters. Otherwise, you probably will get the wrong answer. So if you're not doing a dilution, you need to make sure you do convert it. Now, sometimes people don't realize that perhaps, this is going on. So let's just take an example here, and we're going to make from a table, we have reagent A that has 1 molar. We have reagent B that's 2 molar, very creative, I know. Reagent C that is, I know, I was gonna go with 3, but now you made me embarrassed to do that. So I'm gonna go with 0.5 molar here for this. And let's just say we're gonna make a bunch of test tubes, right? Using this stuff. We got test tube 1, test tube 2, test tube 3. And maybe in this one we use 5 milliliters of this guy, and maybe 4 milliliters of this guy, and maybe 1 milliliter of that guy. And then for this one, maybe we use 6 milliliters, 2 milliliters, and 2 milliliters. And maybe for this one, we use 4 milliliters, 4 milliliters, and 2 milliliters. So let's just take test tube number 1, right? So I'm going to take test tube number 1 and I'm going to make it, right? And I'm going to put in there my 5 milliliters of A. I'm going to put in there my 4 milliliters of B. And I'm going to put in there my 1 milliliter of C, not drawing the scale up. Right. So now I want to know, right, what is the concentration of A? What is the concentration of B? And what is the concentration of C in that test tube? Is the concentration of A in that test tube 1 molar? Not everybody at once. What do you think? All right, how about B? Is the concentration of B 2 molar? The answer is no, it is not, because you just did a dilution without maybe realizing it. When you put all these guys together and you mix them, you've now made a new solution that has a new volume. In order to get the proper molarity of A, you need to use something like M1 V1 equals M2 V2. So if we did this for A, for example, A's original concentration we threw in there was 1 molar, right? We used in test tube number 1 5 milliliters of A. We're trying to find what is its new concentration. Now, V2 is the total volume. What would be my total volume in this case? In a test tube. 4 plus 5 plus 1 is 10 milliliters, right? That is the total volume. So the concentration of A in that test tube, once it's mixed together, is actually 0.5 molar would be my concentration of A. You would also have to do that for B and C. So remember that this is the stock concentration of that solution, but once you start mixing it with other solutions, you're actually doing a dilution. And there is a ton of experiments and stuff that we do where you need to figure out the concentration of your solution in the mixture. And people don't recognize that it is actually a dilution you're doing. In fact, I think maybe on Tuesday, part 2 of the first experiment, you will need to do that as well. So if you have a table like this and you're putting things together, M1 is probably the original concentration, V1 is how much you used of it, and V2 should be your total volume that went in the beaker, the test tube, whatever it is, when it's all mixed together. When you solve for M2, it'll give you the concentration of that guy in the mixture. Any questions on that there? Well, that is Chem 50.